Thank you very much for the introduction. So actually, my talk is more about evaluation metrics than the fact that we're working on news recommendation. But still, let me introduce the problem that we are looking at. So the problem that many newspaper websites today have is that people come to their sites from portals like Google News, for example, and they typically just come there for one article and then disappear again. Now, if you want to sell advertising, then that's not a good situation for you because you only sell the advertising on that one page. So you would like to make recommendations that keep readers on the site. Okay, so you like to keep these readers reading articles, and the way you do that is you personalize recommendations. You give them, in fact, many of the news sites, they give lots of recommendations all over the place. And so you would like to give personalized ones, and our recommendations on this site of Le Point, for example, figure here in this green box. These algorithms that you use to generate those, they need to be tuned, right? There are different parameters you can set. We have seen that in some of the presentations here as well. You're looking at popularity varying over time and so on. So when you tune these, you have to somehow evaluate how good a certain algorithm works. And the best way to do this is to do it online, which means that I evaluate how the users behave when they are actually exposed to my recommendations. And the only problem with that is that I have to test every algorithm and maybe every parameter setting separately. I have to let it run for a couple of days, maybe until I have enough data to really evaluate what's happening. So that's very costly, and I have to spend maybe a lot of time with suboptimal algorithms. So what we do generally in the research and maybe also industrial community is to work with offline behavior. So we look at behavior data from users when recommendations were not present, and we'll see if our recommender system can somehow reproduce these things. Now, quite obviously, this is very different because we are testing whether we can recommend things that users have seen anyway, right? And so in a sense, we can expect to maybe not generate the best recommendations, but it's sort of the best thing we can do, knowing that, though, that online performance is not the same as this offline performance that we're optimizing for. So there are solutions for this, and one solution, actually the only one really that I know of, is the one that was published by a few people from Yahoo, in which you collect logs with random recommendations. So you make random recommendations, and then when you have a certain browsing history, remember we are doing session-based recommendations, so based on the articles that a person has seen, we recommend the next article to look at. We look for log sequences that match that same sequence, and we see which recommendation was successful in there. Since they're random, we'll find sort of all different ones. Now this works for Yahoo homepage because there are only 20 items, but it doesn't work for our news sites where we have thousands of stories, and the random generation will not show enough of them. So that's unfortunately a technique that we cannot use. So back to offline performance. That's sort of the only thing that we can really work with if we really want to tune and look at a lot of different algorithms and a lot of different parameter settings. So this offline accuracy is what usually is looked at in various flavors, and that's basically, does the recommender system predict the articles that people look at? And of course we can test many algorithms at the same time, and but we don't really predict the online performance. And the question is, can maybe richer metrics help? And the idea is here that in the sort of current situation, what we really should be doing is testing all these algorithms online, and it can take quite a while. But this would give us the most accurate evaluation. What I'm saying is, let's go and look at some better evaluation metrics that we can use to evaluate our algorithms offline. So we'll do that without having to have access to a site. We basically look at all these algorithms and we see what they generate according to these metrics. And then we just go to our online site to build a regression model to tell us how these metrics will actually predict the online performance we can expect from these algorithms. Obviously, these metrics will have to make sense for this scheme to work. And we've looked at a bunch of these metrics that have been proposed in the literature. In fact, 17 different metrics. The first group are metrics that have to do with accuracy. So typically, there's like RMSE of rating predictions. There is success at K, and so on. Another one is diversity, some form of dissimilarity of recommendations. Another metric is coverage. So are all items recommended? Do all of them accessible to the recommender? Serendipity, which is some mixture actually of accuracy and unexpectedness, so non-popularity. And then there's also novelty, whether the recommendation is really a long tail item. Is it something that's not very common? So these metrics, we looked a bit, the reason why we grouped them into these groups is that we could see that for these different groups, we would find very little or not very much correlation except for between coverage and serendipity. So they were kind of the uncorrelated ones, whereas the metrics that we did find inside the group were actually quite correlated. So this is kind of a natural clustering. So we basically just looked at these as 5 different groups. Now the question is, which of these metrics actually predict online performance? And maybe I can make a little test. So who thinks that accuracy is the best predictor? Nobody, I see. Diversity? Coverage? Serendipity? And novelty? Okay, so it's quite divided. You don't really know. And most of you don't think it's accuracy. I guess that's a kind of the thing if I ask this question, you think that it's not going to happen. So actually the thing that I have here is that if I have diversity, so we performed a least angle regression to see how these different metrics in fact entered into the prediction. So we tried to predict the click-through rate from the offline performance, and then you include in there a regularizer that minimizes the numbers of features you're using, and you decrease that and you order the feature by when they enter the model. So with this we see that actually accuracy is only the 3rd most important predictor. Okay? And in fact we have here the versions here that entered. So diversity was the first one to enter, and they are the most important one. Serendipity the second. Actually, a lot of people said coverage and novelty, they actually don't enter that much into that. Okay, so I skipped a little bit ahead. Now, the other thing we can do with these metrics is we can do the offline evaluation. And the offline evaluation shows these trade-offs in general. So we cannot usually get maximum accuracy and maximum coverage with the same algorithm, but we have to somehow mix these things. So here we have a context tree algorithm, which is the one we're using as main algorithm for news recommendation. You can look it up in the RecSys 2013. There's a description of this method. And so we can mix that with a coverage criterion that shows for each recommendation how much this would increase the coverage. And so then here is an example. We can sort of see that we can get the points on this curve here. Actually we can, if we want that maximum accuracy, we're going to end up with a fairly low coverage, and then we can sacrifice a little bit of accuracy, we can get more coverage. And if we mix this context tree with the most popular expert or with a fresh expert, these are 2 other variants that were also described in that earlier paper, we get these other curves here. So we can achieve different trade-offs among these different metrics. Okay? And we tested this on 3 data sets. The first one is this CT tree recommender, which was originally running on the Swiss Info site, which is a Swiss news site operated by the Swiss government. And these were nice people. They let us run this for over a year, so we collected quite a bit of data, but it doesn't have a lot of traffic. Then we have the a newer connection with the biggest French news magazine called Le Point. And it's been running there since April, and we've been gathering quite a bit of data there. And we also used the public Yahoo data set, and we distilled it into a form that we could actually use it here. So not all the data is usable as traces. And so the data that we used in the end from Swissinfo, we had 220,000 clicks. From Le Point, we took 5 days and 4.5 million clicks. And the Yahoo data is over 16 days and 573,000 clicks. So, right. So now we come back to this prediction of the online CTR. So the idea is now, as I had in the picture before, basically we measure the performance metrics of different algorithms on offline data, and then we apply a regression model to predict the CTR from those performance metrics. And it turns out that this is actually quite accurate. So when we're trying to predict the click-through rate of the online behavior of a CT algorithm, we can do that with just about 0.5% RMSE. And this is done on 4 measures together, which was accuracy, diversity, coverage, and novelty, I believe. It's in the paper otherwise. So those gave the best prediction results. And so we can see here the solid curves are the ones of the actual observed click-through rate, and the dashed ones are the ones that were predicted from the offline behavior of these algorithms and the continuous measurement of the offline behavior, which was done on the sessions that didn't involve any clicks on recommendation, so we could take those as offline behavior. And so we see here 3 different phases. The first one, we say prepare. It's actually a phase in which we need to gather the data to make these things run. So if we want to use a most popular recommender, so which only recommends always the most popular news stories, then we need to first let it run for a while until we know what these stories are. So in the beginning, we're not very good at that, so we get a fairly low click-through rate. Similarly, for the context tree recommender, we need to first learn what are the stories that people prefer, and that again means that the click-through rate takes some time to increase. Then we have a training phase in which we actually are training the model, and what we're showing here in the prediction is the continuous evolution of those models. So they start with a kind of a default setting. And then the last part we used for testing, which is where we get the numbers and we see that, in fact, we get a relatively low prediction error in the end. So this is just one example on one version. The errors that are shown in the paper are an average over a lot of different variants of these algorithms. Okay, so what we can do with this, the first use, then to repeat, is to say that we are going to use these evaluation metrics to perform an offline evaluation of those algorithms. So what we need for that is to collect once offline data, that is data about the user behavior when no recommendations are present. Okay? Which actually in this case we gather just by taking the data from sessions where no recommendation was used. And then we do a second time we have to go back to get real data, which is to build regression models that allow us to predict actual online behavior based on these evaluation metrics. And the hypothesis here, which I can't stress enough, is that these metrics actually make sense. So if these metrics actually are not good for predicting online behavior because they have nothing to do with what influences people, then of course this is not going to work very well. If they're very good, then we can expect fairly good behavior. And so we used these 17 metrics, and we really went through them to find out which are the best ones. You can find details about that in the paper. We believe we get pretty good results actually at predicting these click-through rates. These metrics were formulated by many of you in the community, so you've done, in that sense, a good job. Okay, and the third thing then, of course, would be that once I have this set up, I can pick what is the optimal algorithm, what are the best parameters for tuning this, and I can take all my time to do that. I can evaluate as much as I want on this offline data, and I don't need to go back to online testing. Now, we can also become more ambitious. So we can think that maybe the best mix is not always the same. You know, on a news site, on the weekend, people maybe want to read different things than during the week. You know, on the weekend, you want to read more about sports or other things. During the week, you want to read about the stock market. So maybe there's a temporal progression as well. And maybe we want to learn different regression models at different times and adjust dynamically. So we tried that as well. It's more ambitious because we need to run this regression more continuously. But we did that with Le Point, and here's only it's more of a preliminary test, which was only done on 4 days of data. So what we show here is the click-through rate for different mixtures of context tree with popularity. So we make a mix of recommendation criteria, and we count popularity with 20, 40, 60, and 80%. That's from left to right always. And this is done in different intervals. So the first one was a Sunday from noon to 10, then from 11 to 6 in the morning, then from 7 in the morning to 10 on Monday, and so on. And so the arrows on there, they show the kind of prediction of how we should change the mix in order to get a higher click-through rate. And so we can see here that this is generally not too bad. So we can see on the left here, those two, we want the optimal popularity is sort of in the middle, somewhere at 60%, and the arrows sort of point in the right direction, whereas during the week, people don't want so much popular items, so the arrows always go in the other direction. We have since tested this on a larger scale. We have just preliminary results. They show that this seems to work actually very well, also over several weeks of data quite consistently. So this seems to be feasible to do this. And again, it also indicates that the metrics are actually not too bad at predicting click-through rate. So that's the idea here. We basically do this dynamic selection. Oops, sorry, I'm going the wrong way. Okay, we're coming closer to the end. So we're still running with more data to validate. And in fact, we have gathered quite a bit now that it has been running with Le Point, which has a lot of traffic, so we can actually see quite a lot of differences there. As a lesson, I think we should take these metrics more seriously. When I've seen the papers here in this conference, I think with very few exceptions, people simply focus on accuracy in various forms, maybe also just RMSE of rating prediction. And this is not, in this case here, not even the most relevant criterion. So we should think more about what are actually metrics that influence click-through rate or influence the real life performance of our recommender, that influence maybe the business metrics that we have. And this is really a call for people from industry, because you do online testing, and maybe you could go a step further and try to characterize which of these metrics that we can test offline actually have an influence. And maybe we can also then search for better metrics. Maybe diversity, the way it's characterized, is really quite naive. And we could imagine that diversity somehow takes into account the kind of item you're recommending. And so there could be different degrees of diversity and so on. And then maybe they would give better results when we try to work. And again, this is something that maybe is a research topic for people in industry who have access to this data. And it would make it open up maybe to the academic community the possibility of optimizing algorithms for something other than accuracy, maybe taking into account this trade-off between diversity and accuracy. And I think there's a whole space of research here that hasn't really been explored, because people never looked at this quantitatively. We always just say, you know, yeah, more diversity is great, but how much more diversity should we trade off against how much accuracy, right? So, by the way, these models, this regression model and offline model, they still depend on the domain and the user population. So if you're thinking that, wow, we could just take this and come up with a new criterion that measures performance across the board, that's not the case. So it's going to remain some kind of a multi-criteria issue, and depending maybe even on the time of day, the trade-offs may be different, right? So, but taking into account these multiple metrics will actually maybe allow us to make much better predictions about how well our systems perform, and also develop much better systems. We're optimizing algorithms, all the machine learning techniques optimize algorithms according to a performance criterion, and the better we can get that, the more realistic it is, the better these algorithms will be. Okay, to conclude, so just to summarize, we have shown a way to evaluate online performance of recommender systems with less data. We no longer need to go back to A/B testing all the time. We can do quite a lot in offline. We basically need to collect data only 2 times. The hypothesis is that users want a certain trade-off of different metrics, of performance metrics, and it's maybe sufficient to evaluate this trade-off to know, what do you mix, what's the right mix in order to get what users want. And as a lesson to the community, I think we always knew that diversity, novelty, and so on were important, but now we can really see how to make use of them. Once we quantify them, it becomes a useful concept. Thank you very much for listening.
Questions? We have some time for questions.
Hi. For that slide talking about that, distributions by different popularity, yeah, that one.
What? This one? No.
The one, yeah, the one has 4 bars. So I think what you said is it looks like the more popular, the less performance. So I'm not sure if you have, maybe you have already thought about, but it seems like the more popular, maybe they're just published longer, such that they received, more exposures, such that, during the recent period of performance comparison, those most popular is actually maybe already, some people already seen it, right? So what do you think?
Yeah, I agree with you. I think you're probably right. Actually, what this shows, just to be clear, so we're not talking here about how popular the recommended article is. It's just about we have a mix of 2 recommender algorithms. One of them is the context tree, and the other one is a pure popularity ranking, where you recommend the most popular ones. And when we rank the recommendations, when we pick out the articles to recommend, we mix the popularity score with the context tree score with a certain ratio. And so that's what this shows here. It's basically just the tuning parameter of the algorithm. And probably you're right that, recommending very popular things is not that great. We, by the way, see that also in the curve, that we are almost twice as good with the context tree than with the most popular recommendations.
Thank you for a nice talk. Could you tell me if you tried this offline A/B testing with online A/B testing, and if results agreed or not? But so you're just reporting that CTR is predicted very well, but what about model comparison?
Oh, this can be totally different. So we had the paper at RecSys last year, where in fact we showed that in some cases you get exactly the opposite ranking in the offline evaluation versus the online evaluation. So that was the case actually on the Swissien 4.1. So with the regression model we are correcting this. So,
Have you some models that works similar with offline A/B testing and online A/B testing? So if I can use this offline A/B testing, I will use, but I don't know agree with online.
Yeah, that's the thing. It very often doesn't agree with the online testing. And so you should do some tests to see which metrics, I mean, that's what we did here, basically to build a regression model to map the offline testing to the online prediction. And so that can correct then the error that you have in those different metrics.
Thanks for the talk. It was very interesting. And by the way, I'm in industry. I'm very interested to talk to you about maybe we can figure out some ways to further this kind of research. It would be very valuable for us. The thing I was wondering about is to what extent do you think that the predicted performance of these algorithms is going to depend on context, whether it's what type of page it is, or what type of session it is, or any kind of information like that we can have.
Definitely there'll be this kind of dependence, and so when you train this regression model, maybe you will have to train different ones for different contexts, right? So that's an open question. And maybe the context will have to be one of the features that you bring into this regression model as well, simply. So definitely, yeah. I mean, the user interaction definitely is another component in here. What I'm talking about is the algorithm itself as well. There's not one unique best algorithm, but it really depends on what your population wants as trade-off between diversity or other metrics and accuracy.
Hi, thank you for the talk. I wanted to ask, so to which extent do you think this could be generalized for all kind of news recommenders, and if it's possible to state something about the results that you have obtained?
You mean like a general lesson, or well, for that this is really a first study. Being a university, it's difficult for us to get access. So getting these Swiss info people to run our recommender system, it took quite a bit of convincing. And these are people who, like us, work for the government, so they're kind of open, to talking. The Le Point people, it also took like 6 months to bring the system online, and it's a lot of effort. So it's difficult to get more sites to work with us. I think what I'm trying to do here is to stimulate some interest in this kind of study, and I think it's not so difficult to do for people who have actually live sites to go, instead of just doing the online testing, maybe also go back and try to see what would you have gotten if you tested these algorithms offline. And if you just record these data points, in the end you can build models that allow you to maybe just use the offline testing, maybe just as a first filter, right? It may not be perfect, but could save you a lot of work. There's somebody in the back there.
Thank you for this very interesting talk. I'm involved with a group that's organizing the Clay newsreel competition. So obviously I'm very, very supportive of this kind of research, and also was very interested in and happy to hear your talk. Our experience has been that it's difficult to actually do online testing. People are afraid of it because of the engineering effort, and afterwards they're also afraid of it because it's difficult to publish results. Do you have any tips about that? This is of course a bit of an advertising plug for Newsreel, and you saw my tweets about the flyers out there. But could you speak to like the sort of ways to push ahead in light of possible more engineering effort than necessary, or creating research questions that are really interesting in the online area?
So the people that run our system, we don't tell them that we're doing A/B testing. They just want us to run the best system all the time, and they would not agree. So we are very quiet about this. I think I see it's really a problem, because you go to them and you say, oh, we're going to do some testing, with maybe suboptimal methods or maybe even random recommendations. they're not going to like that, and they usually, so you have to be a bit quiet about it. I don't know about our colleagues in industry how you do this. You probably have this issue as well, that. But there's really, if you really want to find out what works and what doesn't work, we do have to somehow do it. And one argument one can make, though, is if you have a technique like this one here. We have arguably a faster way of converging to an optimum. So if people are talking about bandit methods, for example, where you kind of randomly explore around, these methods are going to be a lot faster. If we have these gradients and we can search with a gradient, you will speed up a lot more, and so you do a lot less useless testing. So this should be an argument.
Okay. So it's nice to see you're able to get pretty good accuracy for the online metrics using the regression model. But does it generalize to the future data? Because the ultimate goal is trying to see whether that model will be able to sustain, in the future new data, right?
You mean does it work over time or for different sites? Or
yeah, so they say, you learn a model that you get some, weights on, different metrics, but that's all, on the old data. But you cannot say train the model every time because you don't have the data in the future, right? So do you see that model stabilize over time?
More or less, we do see that is the test with, if we go over time here, we do see that there the trade-offs change. And so they can change over time, yes. And so I think there is some model that more or less maybe is an average model that stays stable, and you can definitely gain also by adapting it over time. At least for news sites, definitely there's a cyclical behavior. We've seen that also in other presentations for news and TV.
Okay, I guess that further questions we'll have to take offline. Let us thank our speaker again.
Thank you very much.
Hello everyone, thanks for sitting here still now. So my talk is about content-driven user profiling for comment or the recommendations of news articles. So this pretty long title has two main parts, that content-driven user profiling and comment or the recommendations. So I'll explain these two terms. This is a joint work with Trapit Bansal and Chiranjeev Bhattacharya. We are from Indian Institute of Science. So start with, user-generated content has drawn a big deal of research interest recently, and comments are one of the big source of user-generated content. So we focus on the comments here. Comments are found almost everywhere nowadays, maybe news articles, over around 15,000 comments on a news article, maybe tourist attractions, around 35,000 comments, maybe products. So what it says that the comments denote a active user engagement. So a people who is commenting on something shows that he is interested on that item, even if he does not like that. And sometimes comments give direct feedback. A product, the feature, I do not like the retina screen of this mobile device, something like that. So comments have very rich information and how we can utilize that. One of the broader question is that how we use this user-generated content to engage users more actively. Are focusing on comments, so we want to understand what makes a user to comment. And if we want to understand this, so maybe we want to utilize that for, can we recommend users to comment? And in turn, we use increase the popularity of the site or engage more users or increase the time they spend on the site. So, although these comments have very potential research interest, but recently there's not much of work done on comments on the minute level. So mostly they are focusing on like matching comments with the sentence on the supervised method, or ranking comments in an article, or summarizing the comments in an article, detecting spams. All gross level questions have been answered. In the last year wisdom, in our work, we are trying to understand one minute level question about the comments. So how these comments relate to the news article. So this what we observed that the users who are commenting on a news article, So he may be commenting on the entire news article, or he may be commenting a specific part of the news article. So for example, so if you look at this example, anyway, so if you look at this example, this left side is article and the right side is comments. So this article, I have used the color codes. So different sentences using the color code says the topic of that sentence, and right hand side the color code of the comment shows that which part of the article it links to. So for example, one person commented on the heartbeat reader, or one person commented on the USB port. So although this is a review article of a mobile phone, the people are interested to comment on specific parts. But in this work, we did not consider the users actively. So in this paper, we want to understand the relationship between article, comments, and users. So how these comments are, how users play a role in making these comments. What are their interests? How do we model their interest? And that is how we want to address this question of comment or the recommendations. That is to recommend the news articles which people will like to comment. But the challenge of this problem is that one of the simplest approach using machine learning can be that we tag, use some label data that this user is interested in this kind of news articles. But the problem is that the data set is everly increasing, and all the time different topics come and all new users can join. So it is not feasible to use a label data to unsupervised approaches. Another problem is that the cold start problems, that as the new articles are coming up and it maybe starting a new topic, and it becomes difficult to model the past content with that. And that rules out the vanilla probabilistic metric, positive matrix factorization methods. So how do we handle this kind of challenges? So we take the route of unsupervised methods, that we do not need any label data, first of all, and we can consider the past activities based on the contents, which is very important here to model the user's commenting interest. And that leads to our main approach of content-driven user profiling. So how do we build the user profiles is that the users can be interested in commenting on an article if he's interested on the whole news article or in a specific part of the news article, or if he finds out some of his friends have commented on the news article. That means sharing commenting patterns. So how do we consider these three different aspects into the user profiling? So that is the task that we'll address. Now let us understand how past commenting activity can impact or can help in predicting the future predictions. So if somebody has predicted on, somebody has commented on the heartbeat reader, or maybe has commented on the USB port, he might be interested in commenting on similar aspects in some other products. Or if he is interested in generally on mobile phones, so there can be different aspects of his interest in commenting a news article. So for example here, so this user Bob, he has commented on only the USB port of the mobile phone, and user Alice has commented on some other part. And there are other users who has commented on in general the article, or there can be some users who has commented on some totally irrelevant things, maybe like spams. So users can comment generally, or so how do we drive these things for user profiling? So this topic of comments, we try to model the topic of the comments that they made in the past, a general topic of the article, or specific topics of the articles, a topic of the specific parts of the article. And the baseline is collaborative topic regression. So this the abbreviation we are using is CTR. So what this work is about, that this combines the collaborative filtering with topic modeling, and is a state of the art which can considers the cold start problems and the content together. So this approach is based on topic modeling, and topic modeling is a probabilistic model which can model the textual contents of articles. But the limitation of this work is that it does not consider the comments. The architecture of the model is that it's not trivial to extend the model for the comments. And that fails to model that specific interest of the users. Or if a user is interested on some comments of some other users, or his comment is about the specific part of an article, so these things cannot be modeled. And one of the major challenge is that as I was talking about the comments, so the words are very diverse compared to the standard news articles people, and there is a very low correlation between the words of the comments and the news articles. So how do we address these challenges is one of the major contributions. So we propose that collaborative correspondence topic model in this paper, which combines the topic modeling, correspondence modeling. Correspondence is about the modeling the relationship between comments and articles, and collaborative filtering to model the co-commenting patterns. And after we compute the scores, then we rank using a Bayesian method of personalized ranking. So in short, so we want to compute the score R for user I and document article D. And so this overall score has three main parts. One is the popularity of the article, another is the content of articles as some specific parts, and the content of the comments. I mean, which are the comments are present in that article. I will not go into the details how do we compute these scores. So these scores are computed based on probabilistic model extending the topic model that is based on the CCTM or collaborative correspondence topic model. I request you to look into the paper for details. But one key idea in this paper is using of multiple topic vectors. So in topic models, so these topic vectors gives a probability of the topics for an article. Now in standard methods, they use a single distribution or single proportion over topics for entire article and the comments. And that makes them enable to model the variation across the sentences. For example, if somebody is interested in the USB port or heartbeat reader, and which may be described in only one sentence of the entire review article, so that will have very low probability. But this topic may be very highly probable in that sentence. How do you, so this, for example, this red sentence, so this red sentence may be only one sentence in the entire article, which may be very low probable, but there are many users who are interested in that particular aspect. So we want to vary the proportion over topics across the sentences. And we use that using multiple distribution over topics across the sentences and across the documents and the comments. So that makes the proportion over topics to vary, and maybe the correlation that user curl who is commenting on the red and the red sentence, so this correlation may be very high, whereas the comments of the user curl may be the correlation may be very low if you consider the entire article. So MTB allows to model that aspect, but one of the challenges is that how many topic vectors do you use? Suppose you use a very large number of topic vectors, that will induce a very high amount of variation, which may not be suitable because there can be some articles which are maybe coherent and people may like to comment on the entire article as a whole. So this imposes a challenge in modeling this idea, and how do we use efficient inference method to compute these scores. So what we did is we used a Bayesian non-parametric pair over these topic vectors. I do not talk about the details here, please look into the paper. And what the elegance of that method is that we could derive an efficient collapse-gift sampling inference, which is as efficient as using a single topic vector. So that makes it very suitable in our scenario. And another challenge was that suppose as new news articles can come up quite often, then suppose user Mark wants to comment on something new like health app which has appeared, maybe he has seen for the first time, but he does not have any previous history for that. So how do we model this kind of novel activity? So we incorporate the latent offsets concept into this topic modeling to handle this situation. The inference, because of this, all the dependent parts becomes hard, and MCMC does not apply directly. And we need to work out a hybrid inference mechanism based on MCMC and expectation maximization. Coming to our evaluations, so we have used 3 datasets on real-life news and blog datasets, and one is the Ars Technica Science blog and Ars Technica Gadgets and Daily Mail Sports. So, for example, Ars Technica Gadgets, there are about 100,000 comments and 4,000 users with 3,000 articles. And how we evaluated our method is that we held out 20% of this data randomly, and then we use one of the first metric to compare is the perplexity. How do we accurately predict the held out data? So we use the baseline of correspondence LDA, which is a state of the art for modeling this kind of dependent datasets like news and comments. So we say that in all the 3 datasets, our method is more accurate to predict the held out or unseen data, but our main task is to model the user's commenting interest and the recommendation task. So how do we do? So on that task, so we compared using 3 baselines. One is the tag CF. So this work is considered only the tags associated to the articles, and based on these tags they recommend. Another is this collaborative topic regression that I talked before, that they combine the collaborative topic model with the recommendation. And another approach is the content-only topic model. This is a specialized version of our model which considers only the content and does not consider the co-commenting patterns. So we consider the area under curve of ROC, and we compare in warm start and cold start in both the situations, and in both the situations we see that our method is outperforming all other methods, and interestingly only the content only method is performing quite well. And this is significant is because this shows the importance of the content. Even if you are using the CTR, which is the state of the art, it outperforms in some cases just modeling the contents of the comments and the articles. And if another method is to comment the sparse commenting scenario. For example, if for users who have less than 5 comments, so how do we model their commenting interest? And if the articles have less than 10 comments, so this kind of heavy-tailed situation, how do we model this kind of things is modeled suitably for CCTM. That's we used again that area under curve. And we see that the CCTM or our proposed method is outperforming other methods quite well. So this shows that again shows the importance of the content and how the content, based on the content, how we can model the user's commenting interest, and that can be effective in recommending. Thirdly, we compare using the ranking. So here we use the hit rank at 5, where CCTM is 165% better than tag CF and CTR on all the 3 datasets. Now coming to the conclusion, so our main conclusion is that the recommending comments on can enhance the user's experience. You can recommend a news article that may be interest of the user, and that can increase his satisfaction to the site or users. And users may find this may help also to remove the spamming, reduce spamming comments. And content-driven profiling is very useful in this respect. Thank you.
Any questions?
So first, very interesting work. One data set that was a little late for publication time, but is not in there, is Ars Technica Gaming, August 2014 to July 2015. And some interesting events happened at that time. But where I'm saying with that is, sometimes it seems like maybe we don't want to recommend the article the user would actually want to comment on when, for example, the user is a troll. And maybe they like going and trolling articles on some topic, possibly with abusive content. And a standard collaborative filter is going to say, yes, our user should comment on this article, but really you don't want them to. So first, two questions from that. One, does your current topic modeling approach do anything with, is it capable of perhaps capturing trollish signals or maybe some sentiment? And then the second one is, do you think it might be better to try to build that into this model or deploy this model alongside a separate troll detection system to just get those people out of the system?
Yeah, very good question. So by sentiments, we are trying to model the commenting interest. So this is a very hard problem, and we are just trying using the past his commenting behavior as a proxy of his sentiment or the commenting preference. Now, if you use some other, the more information you use about the user, that will improve the performance. But this just shows that his past commenting content or commenting nature can itself be quite useful.
Hi, thanks for your talk. Do you feel, after, like at the end of your paper now, comments based on a specific domain, so comments for music or comments on movies can be used to recommend things cross-domain, as opposed to, you have comments that you analyze for news right now, right? Can you use that information to recommend stuff that are in a different domain?
So, for example, somebody, you have training data for sports, and do you want to recommend for movies?
Yes, exactly.
Is it your question?
Yeah, so for example, it's a sports, so a person's been commenting a lot on soccer, all right? And can that information, do you think, can also be used to infer that, okay, this person might be interested in events?
Okay, so the basic assumption in our model is that the people who have commented and that their comments reflect their commenting interest. And if somebody we have the information about his commenting preference on sports, that may not be similar what is commenting preference for movies, for example. And it is not that easy to transfer the knowledge to another domain. So you can have the co-commenting patterns. For example, a close group of friends, they are maybe interested in both in movies and maybe both in soccer. But this is a very personalized track. So if you may be very interested in some kind of sports and maybe a totally different interest for movies. So we need to have the past information. And based on the past information, we have to propagate for the prediction. So it's not very easy. And maybe this method directly will not apply, but I don't have any answer. How do you transfer the knowledge to another domain?
Yeah, thanks for the interesting presentation. Actually, as far as I understood, when there are comments from the users on an article, it's kind of like a plus for the article. So I think you referred to that thing as like a comment trustworthy article. But what if that comment shows like the negative impression of the users, like, or positive, because it's like the assumption is that all of them are positive, so they are good, that this news has like lots of comments or something like that. But what about if some user disliked the news or the article? So have you ever taken it into account or as like future worker?
Yeah, this is I think another good question. So what you are saying is that so what our assumption is that if somebody is not giving any comment, is maybe ignoring the news article or may not be interested at all. And if he is commenting, he may like or dislike. Even if he dislikes, for example, I did not like the heartbeat reader of Samsung S5. But he may, I mean, he was interested enough or he had enough time to spend to give that comment. And maybe in some other article, if he has similar features, he may be interested to look into that article. Or that is the basic assumption. And even if there is a negative sentiment, that does not mean that he is not interested. So he may be interested, and that is why he spent the time. That is the basic assumption.
Hello. Do you model the user may change their interests during time, right? May be interested in some technology today, and 1 year ago I have other interests. Do you model this kind of decay on the interests or change in the user interests?
Yeah. So as of now, this model works only with the static part. So it does not consider the evolution of users' interest over time. So one thing that we consider here is that when news articles are coming, and that people, somebody is using, suppose Mark has seen some app like on health app for the first time. How he is going to react on that? His past commenting interest is not going to show any clue or any information about this. So for that we have used this one method of this I forgot. So in the topic in our model, probabilistic model, we have one parameter to vary from the past inference, but is not. So if you just forget the past information totally, and then you cannot model it accurately. And if in the dynamic situation the content totally changes, then it is like similar to a situation where you do not have any past information. So then also this model is not going to work that well. So the basic assumption is that the past experience is helping to predict the future.
Okay, so if there are no more questions, let's thank our speaker again.